Welcome to this explainer. Okay, so today we're tackling a topic that honestly sounds kind of intimidating at first: basic physics and fluid mechanics. But don't worry, we're going to completely strip away all that heavy, boring scientific jargon. Instead, we'll use natural, everyday language to make these concepts really stick. Think about it. If you've ever poured a simple glass of normal pani or struggled to get some stubborn shahat out of a jar, well, you already intuitively understand fluid mechanics. Today, we're literally just putting the official names to those everyday actions. So let's dive right in.
Here's a quick look at our roadmap for today. We'll start with fluid mechanics K basics. Then we'll hit viscosity, yani gaadapan or resistance. Next is velocity, which is speed with direction. Fourth, we've got volume or space kitna ghera. And to wrap it all up, तीनों concepts ek saath.
All right, kicking things off with Section 1, Fluid Mechanics Key Basics, in simple language.
Let's jump straight to our first major concept here: viscosity, yani gaadapan or resistance. So what is viscosity really? It's simply a fluid's property that actively resists its own flow. And this happens because of friction between its layers. Simply put, it's just a liquid's natural gaadapan, or stickiness. I want you to picture a fluid not as one big solid block, but kind of like a huge stack of microscopic sheets of paper. When the fluid flows, those microscopic sheets have to slide over one another. And that sliding, it creates friction, or rugged. If that internal friction is super high, the fluid is thick and stubborn. If the friction is low, it flows effortlessly. So the absolute key takeaway here is that viscosity is literally just internal friction slowing things down.
Let's look at a real-world example. On the top, we have high viscosity, apna normal shahad. Because of that high internal friction we just talked about, its layers are practically grabbing onto each other, right? So it flows very, very slowly. It has extreme gaadapan. Now on the bottom, we have low viscosity, normal pani. There's hardly any internal friction there, so the layers just slide past each other effortlessly, flowing super quickly. It's truly that simple. You know, the next time you're squeezing a plastic bottle of shahad and just waiting for it to drop, you are literally experiencing high viscosity and internal friction in real time.
Moving on to Section 3, velocity, which basically means speed with direction. You know, people often use the words speed and velocity interchangeably in casual conversation, but in the world of physics, they are entirely different animals. Speed is just a raw number. For example, a car is driving at 60 kilometers per hour. That's it. You know exactly how fast it's going, sure, but you have zero clue where it's actually headed. Velocity, on the other hand, absolutely must include a strict direction. So, a car is driving at 60 kilometers per hour towards the north. See the difference? Velocity is speed with a mission. So the crucial thing to remember is that velocity gives you the complete picture of movement. If a fluid is rushing through a pipe, its velocity tells us not just how fast it's going, but exactly which way it's flowing.
Just to keep our foundation solid, here are the standard units we use to measure velocity out in the real world. You'll typically see m/s, which is meters per second, or km/h, which stands for kilometers per hour. Don't worry, we aren't going to get bogged down in heavy math today. Just keep in mind, whenever you see these units attached to a specific direction, you know for a fact you're looking at velocity.
Okay, on to Section 4, volume, or as we can call it, space kitna ghera. I want you to imagine an empty cardboard box sitting right there on the table in front of you. Got it? That empty 3D space inside the box, the absolute capacity of it, that is its volume. Now let's say you take a hose and fill that box entirely to the brim with water. That exact same space is now the water's volume. Volume is just a measure of physical, three-dimensional space. It honestly doesn't care how heavy the water is, and it definitely doesn't care how fast it's moving. It only asks one incredibly simple question: how much room does this fluid occupy?
And calculating this space? It's actually a breeze. It's essentially a four-step recipe you probably learned back in grade school. To find the volume of a geometric shape like our box, step 1, you find the length. Step 2, the width. Step 3, the height. And step 4, you just multiply them all together. Length times width times height. Boom! That gives you the total space locked inside. See? No complex physics equations needed for this one at all.
Now, when we measure volume, especially for everyday fluids, we rely on a few really common units. Liters usually shown as a capital L, milliliters as ml. Or for massive industrial spaces, you might see cubic meters. So think about it. When you go to the store and grab a 1-liter bottle of soda or water, you're actually buying a specific volume. You're buying a strictly defined amount of physical space that just happens to be filled with liquid.
And finally, Section 5, Tino Concepts Ek Saath, our masterpiece finale.
All right, I want you to pause for a second and mentally picture this specific, slightly messy scenario. मान लीजिए आप 1 लीटर शहद फर्श पर गिराते हैं. Imagine you accidentally drop a full 1 liter bottle of sticky honey right onto your kitchen floor. What actually happens next? Think about the 3 V's we just covered. How does the space it takes up, its sheer thickness, and its movement across the tiles all interact in that exact moment?
Let's break down exactly what's unfolding here. First up, volume. That puddle on the floor, it takes up exactly 1 liter of physical space. Even outside the bottle, it doesn't magically become 2 liters, right? It occupies the exact same volume. Second, viscosity. The honey intensely resists spreading out. Because of its high Gaudapan, or that high internal friction, it creates this thick, stubborn mound instead of instantly splashing everywhere like water would. And third, velocity. Because that super high viscosity is holding it back, as it slowly creeps across your kitchen tiles, its velocity, its speed pushing outward in every direction, is incredibly low. It moves forward very, very slowly. So in one simple, admittedly annoying spill, you are witnessing volume, viscosity, and velocity all working together simultaneously.
The absolutely crucial point is this. Physics isn't just trapped in heavy, boring academic textbooks. It is alive and kicking in every spill, every flow, and every single movement around us. Once you grasp these foundational terms, you literally stop seeing just a messy floor that you have to clean up, and you start seeing fluid mechanics in action. You start seeing the mechanics of the everyday world in high definition.
I want to leave you with this final, thought-provoking question to test yourself with later today. The next time your morning chai accidentally spills off the table, don't just immediately grab a towel. Ask yourself, what is the exact volume of that tea? What is its viscosity compared to that honey we talked about? And what is its velocity as it drips down onto the floor? Try to spot the physics hidden in your everyday life. Thank you so much for joining me for this explainer. Keep asking questions and definitely keep exploring the amazing physical world around you.